Thank you. Okay, so we are going to continue from last time. I recall we have defined some algebraic structures. We said that if the associative law holds in a binary algebraic system, so it's called a semigroup, and if it has a neutral element, it is called a monoid, and if all elements are invertible, meaning that any element has an inverse, which means that together with the operation, we get back to the identity. I mean, we call it identity, it's the neutral element, then we call it a group. And if all operations, I mean, all elements commute with respect to the operation, that it will be commutative, or in our name, abelian. Okay, and we have seen some examples, also examples of subgroups. Okay, so a subgroup, it's like a subspace. I mean, subspace is a particular case. It's a subset which is which satisfies all the properties of a group. I mean, it's a group. Okay. Okay. Yeah, I'm just recalling you. We had general linear group. This is all matrices with determinant, I mean, not zero, and here all determinant are one. Or for example, here the operation is multiplication of matrices. Here the operation is just plus. So we take it doesn't have to be free. I mean, any multiplicity of Z will be a subgroup. For example, this one. Okay, so these are subgroups. Okay. So now, I mean, our direction is towards what we call number theory. Once we get some knowledge on number theory, then we will be able to translate it to some applications in cryptography. Okay, so this is our main direction. So let us have some more knowledge on group. Okay, so okay, and now I'm going to give you a definition of a group which plays a major role in number theory. Okay. The algebraic structure consisting of Zn, I mean, we are going to call it Zn, sorry. It consists of remainders of numbers modulo sum n. Okay, so we have this class and this class. I'm going to explain, okay? But first we have to write it. Of course, we have also the zero class. Okay, so 0, 1, 2, and we finish by n-1. This is with respect to plus modulo n. Okay, this algebraic structure is called the congruent group, or remainders modulo n. And now I'm going to explain what is this group. Okay, so we just take all integers, all elements in Z, okay, and we look at the remainder when dividing. I mean, when taking out multiplicities of n. Okay, for example, what is Z3? So Z3 is just all numbers that are 0 modulo 3, which means that are being divided by 3, and all numbers which are 1 modulo 3, which is 4, 7, etc. Okay, and 2 modulo 3, okay, which is 2, 5. Okay, so 5 is also here, and 4 is here. I mean, any class here contains infinitely many numbers. And so this group has only 3 elements, but each element is an infinite set of numbers. And this is taken together with the operation of plus modulo 3, which means that we take some representative here. For example, what will be 1? So we are not always going to write these brackets, okay? We just know that we live in Z3. So in Z3, okay, 1 plus 2 is what? What do you say? 1 plus 2 is?
0.
0. Oh, okay, okay. So in other words, since 0 is the neutral element, so the inverse of 1 is 2, because together with the operation, you get back to the neutral elements. Okay, and the same is for 2, of course. Okay, okay. So this is the remainder modulo n group. Let's see just one more example. If we have Z6. So, okay, so I'm not going to write these brackets again. Okay.
Sorry, why 1 plus 2 is equals to 0?
Because 1 plus 2 is 3, and 3 belongs to this element, which is the neutral element.
Okay, 3 modulo 3 is 0.
Yes, once you get to a number that is a multiplication of 3, then it's 0, because modulo 3 it is 0. It has no remainder.
Yeah, okay.
I have a question about, I know
Yes,
how to call it, maybe notations. In English, you say set. In Hebrew, you say kvutza, right? And in our course, group is also kvutza, but it's
Chavura.
Okay.
Chavura. This is the Hebrew name, Chavura.
Okay, yeah, because I don't think we said it last time. Okay.
Yes. So please let me see if you got it. What is the inverse here of 2? What is the inverse of 2 here?
3.
4.
No. 4.
Sorry.
Okay, because 2 plus 4 is the neutral. Okay. So we are going to use this group many times. Okay. Okay, let us see another definition. Let H and K be two groups. Then we can define their direct product. We write it like this. And it contains all pairs such that the first component belongs to H and the second to K. Together, I mean, it's a group. Together with the element, with the operation of H and of H and the operator of the operation of K. Now, this can be any two groups we just match them together. Okay. So of course it's a new group. Okay. Because what will be, for example, H1 K1, this new operation with H2 K2. So any element goes with the same component. I mean, this will be H1 H2, SIC K1 K2. So this is a group. I mean, what is the neutral element here? The neutral element is the one of H, SIC the one of K. Let us see an example. Z2 direct product with Z3. How many elements you have here now? The answer is 6. And either are 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1, 2. These are the elements in this new group. Okay, I was able to go from 0 to 3 in the second component. Okay, because I taking all remainders modulo 3, and in the first component I was able only to write 0 and 1. That's all. So these are all possible combinations. So it's a new group. And of course, in the first component, this is the operation in Z2. And in the second component, it's the operation in Z3. Okay. We are going to see in a minute what is the importance of these constructions. Okay. So let us just see that we have understood this. What will be the inverse of 1, 1?
One, two.
Yes. You see why? Because 1, 1 plus 1, 2 is 0, 0. Okay, because 2 is 0 in the first component and 3 is 0 in the second one. So this is the neutral element. Okay, so the inverse of an element is an element that takes you to the neutral. Okay. Now we want to talk about the set of generators of a group. So let me begin with a cyclic group. A group G will be called cyclic if G can be generated by a single G in G. What do I mean generated? Okay. Generation means taking all possible integral powers, okay, of G. What do I mean? That G is actually, we want it like this. Generated by G, it means that all elements of G, of a great G, are just powers of little g. By the way, I remind you that a negative power just means you take the inverse and then the positive on it. Okay? This is what it means, negative power. So let us see examples, okay? Okay, so the group Z, infinite integers, okay, infinitely many integers with plus is cyclic. I mean, you can take one element and by taking its powers, you can cover the whole group. What can be a generator of this group? What do you think? What can be a generator of this group? I claim that the number 1 is the generator. Why? What is 1 in the power of 5? I remind you that taking the power, it's not multiplication, is with respect to the operation here. So 1 in the power of 5 is 1 plus 1 plus 1 plus 1 plus 1, it's 5. So it is clear how can we represent all elements here as some power of 1. Okay? For example, 1 minus 3 will be what? What is the inverse of 1? What is the inverse of 1?
Minus 1.
Minus 1. So it is minus 1 in the power of 3. But what is power? It's not multiplication. It's minus 1 plus minus 1 plus minus 1. So it's minus 3. So you can represent any element, any integer by some power of 1. I couldn't do that using 2, because if I was taking a generator, the number 2, I would get only the even numbers. Okay, I couldn't generate the number 3, for example. So this is the generator of the all group. There is another possible generator. What will it be? There is another generator. It can be also generated by
-1.
-1. It's just taking the inverse powers, okay? Also -1, these are the only two elements which can alone generate the all group. So this is a cyclic group. We're gonna see later that actually any infinite group which is cyclic is isomorphic to Z. I mean, once you have established this group, I mean, all the other are just isomorphic. All other infinite cyclic group. Okay, so this is an infinite cyclic group. Okay, another example, which it's Zn, as we've seen. What will be the generator here? Again, 1. But here, when it gets to n, then it goes back. I mean, there is a loop here. Okay. For example, in Z6, okay, what is 1 in the power of 7? Or 8? What is 1 in the power of 8? 2. Okay. And what is the inverse of 1 here? 5. Okay. But you can represent any number in Z6 using some power of 1. So any Zn is finite cyclic group. And we are going to see later that any finite cyclic group is actually isomorphic to such a group. So any cyclic group is either isomorphic to this group or this group. That's all. The all others, I mean, it's just another representation of the same basic structure. Because once you have a generator, the only question is what is order. I mean, we're going to say what is order, but how many elements it can generate? I mean, infinitely or finitely many. That's all. Okay, let us see more examples. If you remember from last time, we have defined this group. For example, omega n. These are all complex number, which in the power of n are 1, together with multiplication. So if you remember, I mean, if you remember from your studying, this also can be generated by one generator, which is cis. Okay, so this is another cyclic group. For example, omega 4 is generated by this element. Why? I mean, by just I. Why? Because I in 0, this is 1. I in the power of 1 is I in the power of 2 is -1, and I in the power of 3 is -I. And then you get back to here, I in the power of 4, you get back. Okay, so this is the group. You can see it on the unit cycle. I mean, you take the first time that it appears. So in the case of 4, it appears first here. This is cis. And then its square will be here. Okay, and then you get back to 1. So the only thing that matters is the first time, I mean, the angle that it will be first time, but then you're going to do n times and go back to 1. So this is also a cyclic. And I claim, okay, that, for example, omega 4 is isomorphic to what? To what group that we have seen? Z4.
Yeah.
For us, these are the same. I mean, almost the same. This is just written in a multiplicative way, and this is in addition way, but it's the same thing. Okay. So what will be the map from one to the other? You just have to take the generator here, going to a generator here. This will be the map that shows that this is an isomorphism. I mean, I will be 1, and once you explain what will be the generator mapping, then all the others are determined. I mean, I square will go to 1 square because this has to be an homomorphism. Okay, I mean, phi of I recall you what does it mean to preserve the operation? To preserve the operation means that if you take A dot B in the source, then it will be phi A, phi B in the target. Okay, so of course phi A K will be phi A in the power of K. This goes from here. I mean, once you understand that you can first do the operation here, or taking the image and then taking the power, is the same thing. I mean, this implies this, the same thing. So I square goes to 1 square because this is the phi of I square. So this is the phi of 1 square. Okay, and by the way, this is 2 and this is 3. And this is what? What is 1 in the power of 4?
0.
0. Okay, because it should have been 4, but 4 modulo 4 is 0. I mean, there is no remainder. Okay, so you get that the neutral goes to the neutral. We're going to see it that it's always like this. I mean, the neutral goes to the neutral in isomorphic. Okay, let us see another example. Okay, I'm afraid that maybe Aviv is in shock. Okay, if something is not
No, I'm
clear,
good. I'm good.
oh, okay. You can fix an appointment with me later, and I will be explaining everything from the start if you want, okay?
Sure, thanks.
Okay. So the following example is very important. For example, we take what is the number example for? We take z, for example, z2 times z3. So we have seen this before. These are pairs, which are 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1, 2. 1, 2, 3, 4, 5, 6. Okay. I claim that this group is also cyclic. Okay, this is being generated by this element. Let us see why. Okay, let us see why. Because if you take, first we have to remember that every element in the power of 0 is just E. Okay, it's like taking in the power of 1 and multiplicative in -1. Okay, so if we take 1, 1 in the power of 0, it's just 0, 0. And 1, 1 in the power of 1 is 1, 1. After that, okay, so this is the power. Okay, this is the power. This is 0, 1. In 2, what does it mean 2? It's 1, 1 plus 1, 1. Okay, so this is what? 0, 2. And then, okay, this is the power of 3. This is 1, 0. I'm always adding 1, 1 to the last result. Okay, and 1, 1 in the power of 4 will be 0, 1. And 1, 1 in the power of 5 will be 1 and 2. And that's all. Why that's all? Because next time we get back to here. If we add another 1, 1. So what do we see here? Okay, that this is a generator of the group. You may think that this is the situation every time that we take direct products. Not at all. Okay, for example, if we have taken Z2 with Z2, this is not cyclic. Okay, there is no generator here that alone can generate everything. Okay, this is not cyclic. For example, if we want to take 1, 1, so in the power of 0 is 0, 0, 1, 1, and that's all. That's all. We cannot go further because the next time we get back to here. That's all. We didn't cover the all groups element because this should have been more than that.
Can you please repeat the previous example? Because
Sorry.
can you please repeat the previous example?
Yes, of course. The group here contains 4 elements, which are 0, 0, 0, 1, 1, 0, and 1, 1. So taking the powers of this element, we reach only 2 of them, not all of them. The reason is that in the same moment, we got the neutral. Why? Because 2 and 2 are not co-prime. Okay, so we are going to talk about it later, but this is the basic of number theory. Okay, we're going to see later that such a group is cyclic if and only if, okay, these two numbers are co-prime. I mean, their GCD is 1. Their greatest common divisor. Okay, so actually, to be able to generate this group, we need actually 2 elements. We need 1, 0 and 0, 1. So it's not cyclic, because cyclics mean you can use only 1 generator, and here you have to use 2 generators. Okay. Another example of a non-cyclic. So this is not cyclic. Okay. Another example of non-cyclic is Z2. What is Z2? Z direct product with Z. So this again will be the same generators from last time. Only here we have only 4 elements, and here we have infinite square. Okay. How did we call it in linear algebra, this set? You remember? How did we call it in linear algebra?
Basis.
Basis. Now, it's not true. I mean, it's a basis over Z. I mean, it's not being generated by this. Why? Because this gives you only the element in Z direct product with the even numbers. You cannot generate, for example, by these generators 0, 6, 1. You cannot, because any power of these elements will give you only even numbers in the second component. Okay, so we have to be careful, because in linear algebra it was over a field, over Q, over R, but here it's over Z. Okay, so we cannot take an half of it. An half doesn't exist here. Okay, you don't have this element half. So if you take powers of these elements, then it's 0, 4 or 0, -2, but you cannot reach 0, 1 here. You cannot. Okay. Now we have this proposition. Let me just use that just in a last example. Okay, if we take, for example, the field Q, and of course we have to remove the 0 in order that all elements will be invertible with respect to multiplication. So Q star will be Q without the 0. and you take it with the multiplication. Of course, it's a group, but it's not cyclic. Not only that it's not cyclic, it's not finitely generated. Okay. I mean, to be able to generate all elements in Q, you need all primes, and there are infinitely many primes. Okay, so we are going to talk about later, but just for example, I mean, there are groups that are not finitely generated. Okay, I mean, you cannot create all elements here by some finite set of numbers, of rational numbers. Okay. Last example. Okay, last example. I want to see you, I want to show you this example. GL2 over Z2. Okay, what is this group? This group is a group of 2-on-2 matrices being invertible, I mean, with determinant which is not 0, and the entries can be either 0 or 1, I mean, coming from this group. So let us write it. This is the neutral element. Now we have this element and this element and this one and this one. These are possibilities. Okay. Is it clear? For example, what will be this element square? Let us compute it. One and 0 is 0, A is 1. 1 and 1, what is it here? 1 plus 1, what is here?
0.
0. And 0 plus 0 is 0. And 0 plus 1 is 1. So it turns out that the inverse of this element is itself. Okay? Because you got here the neutral. But this group is not commutative. Okay? For example, if we take this element multiplied with this one, we will get what? 1 and 1, it's 0. 1 and 0, it's 0. No, it cannot be. 1 and 0 is 1. And 0 and 1 is 1. And 0 and 0 is 0. Okay? But if we take the opposite direction, maybe these are these do commute, maybe. But in general, this group is not commutative. Okay, so 1, 0. Oh, it's just not the same already. Okay, so 1 in 0 is 1. 1 and 1 is 0. 1 and 0 is 1. And 1 and 0 is 1. Okay, let us see that we didn't do any error. Okay, 1 and 1 is 0. 1 and 0 is 1. 0 and 1 is 1. And 0 and 0. Okay. It's not commutative. Why do I mention that it's not commutative? Of course it's not commutative. I mean, multiplication of matrices is not commutative. Okay? I mean, in general, of course, you have matrices that do commute. The reason why I mention it, because we are going to see that if a group is not commutative, I mean, you have some AB, which is not like BA, like here, you see? Okay? Then it cannot be cyclic. Let us write it. Proposition. If G is cyclic, meaning that it can be generated by a single element, then G is commutative, what we call abelian. Okay, we're going to prove it.
This is not an if and only if statement.
Sorry?
This is not an if and only if statement. It's only one way.
This is a statement, a general statement, yes.
Yeah, no, but I'm saying the other way around is not true. If G is abelian, it's not necessarily cyclic.
No.
Okay.
No, of course. We have seen an example. Okay. Q with multiplication is abelian. But it is far from being, it's not
Right.
even finitely generated.
Right. Thanks.
Okay. Okay. So the proof is very simple. I mean, take any, I mean, if G is generated by a single element, then any A seek B in G, A is some power of G, and B is another some power of G. So what is AB? Is GI, GJ. Now, we have the associative rule, so we can use the power rule, which is, now this is the regular plus Okay, that's all. So we could have, I mean, we could predict that this group cannot be cyclic. Okay, this group of GL2Z2 cannot be cyclic. Because if it were cyclic, it were abelian, and it's not abelian, okay? There cannot be there cannot be a matrix here, okay, that generates all the others. Okay, there is no matrix here because it's not commutative. And if it were cyclic, it would have been commutative. So the last thing I want to tell you before we go into the number theory is definition of a rank. Okay. The rank of a group G is the minimal number of generator or of elements that generates together. Okay, for example, what is the rank of Z? This is cyclic, or it is one, but the rank of Z2, okay, is 2. We need here 2 elements. And the same, this is the rank of we can write just Z2 square, as we've seen. This is Z2 direct product with another copy of Z2. And it is also the rank, we didn't see that, but we're gonna see it later, of GL2 Z2 that we have just seen here. We need 2 matrices here to be able to generate all elements. Okay. More general, what is the rank of Zn? I mean, you take that product of n copies of Z. So you have a tuple vectors. I mean, so what is the rank of Zn?
N.
N. And what is the rank of Q?
Infinity? No.
Okay. Questions so far? You know, I don't remember if I told you. I had once a conference in Lyon, in France, and they brought their, I mean, number one in algebraic geometry in the world today. I mean, maybe not number one, but one of is called Brian Conard. And he was writing, I mean, so quickly, I mean, board and another board. And after writing 3 boards, he asked, am I going too fast? Okay. So I remember this moment. I mean, we were all shocked. So please tell me if I'm going too fast.
Okay, thanks.
Okay. So let us now, we are going to see how all these things are gathering together in, I cannot say number theory because we are just in the beginning. So let us do in like in the other courses, introduction. To number theory. I think one of the most exciting things in mathematics, okay, is to be able to ask a question that a general audience can understand the question. So it's a natural question, okay? But the solution to this question needs very sophisticated tools. Okay, this is the beauty. I mean, it's not a problem to ask a question that, I mean, it's you need to be a PhD to understand the question. Okay, okay, so you can always request, but a natural question, I mean, that a classical question, this is beauty. I mean, something that you could have thought, I mean, anyone could think about this question, okay? So this is what we are going to see now, our classical questions. I mean, going back to the Greek, I mean, to has found solutions, modern solutions, okay? So number theory is a very classical issue. Okay. Oh, sorry. Given two integers, A and B, we write A divides B like this. When okay, meaning that there is another integer, okay, not 0, such that B will be QA. For example, 2 divides 6. 6 is divided by 2, but 2 divides 6. So this is how we write it. Okay. A prime number is first a natural number P greater than 1. 1 is not a prime. Okay, it's a definition. So what is a prime number? Is a natural number P greater than 1, whose only divisors are plus minus 1 and plus minus P. This is a prime number. Now we have the fundamental arithmetic theorem.
So I have a question.
Yes.
So this concept will be extended beyond the standard multiplication because, we are familiar with prime numbers on the, I don't know, on the real domain or on the rational, but if we define another operation or another.
Yes, of course. We are going to see, for example, the definition of a prime function or a prime polynomial that is irreducible. I mean, this is the same concept, yes.
Cool, thanks.
Okay, the fundamental theorem of arithmetic is, we know it from school, okay, that any or for any natural number there is a unique up to order of factors the composition into primes. I mean, n is P1, P2, and the only thing is the power. Okay, for example, 6 is okay. Now, it's not obvious that this decomposition is unique. As you said, we can think about domains over which this decomposition is not unique. But our Z or N is what we call unique factorization domain, UFD, but it's not in general true, okay? Okay, so now we can talk about the GCD, okay? Given A and B in Z, okay? Their greatest common divisor, okay, is a natural number, okay, which we denote by this way, okay, that divides that let me read that common is the maximum, is the greatest, okay, is the natural number that divides both. So this is the greatest one, the greatest. For example, GCD, so we write it like this, or shortly, just like this. Okay, this is in short. Okay, for example, 6 and 8, what will be the GCD? What will be the greatest common divisor? What?
2.
2. Okay. Similarly, we define given A, B, and Z, okay, the minimal, or we write it list, the least common multiplication is the least natural integer number that both divide it, okay, and we write it like LCM. This is a C. Or just in short, in this kind of brackets. Okay, this is in short. For example, what will be the LCM of 6 and 8? Okay, I'm searching for a natural number that both divide it, but the minimal one. Of course, if I take 48, okay, the both are dividing it, but I'm searching for the minimal one. What will be the minimal, I mean, the least common multiplication? What do you think?
24.
24. And, okay, proposition. Given A, B natural, you will always get that the GCD multiplied with the LCM, or not only 6 and 8, AB. Will be just their product. Why is it true? This is very simple. We just have to write A as a product of primes. And write B using the same set of primes. And if some prime doesn't exist in one decomposition, then you just take the power 0, okay? So B is Pi beta I, okay? So what is the GCD? If you want to create the GCD, so you must take the least, I mean the minimal power between the two, because you want it, okay, to exist in the factorization of A and B. So you take actually the Pi minimal between alpha I and beta I. This will be the GCD. Okay, because you want this number, I mean, for any I to exist in A and in B. So you take the minimal power. But if you want to look at the LCM, this will be the maximum. Power. We are going to see an example in a second. By the way, maybe alpha is equal to beta. So minimal is the same as maximum. It's also possible. Okay. But then if you take AB multiplied with the LCM, you just get PI alpha I plus beta I, because either this is alpha, then this is beta, or the other direction. But if you take the multiplication of this, you get alpha I plus beta I, which is exactly PI alpha with PI beta, which is AB. Example. Six was 2 and 3. 8. So this is the power 1, 1. 2 was 2 in the power of 3, and 3 in the power of 0. Okay. So if you want to compute the GCD in these brackets, okay, so you take the minimal power for any prime. So the minimal power is this one. This is the minimal. And for 3, this is the minimal. And so it's just 2. But when you think about the LCM, then it's the opposite. Here, this is the maximal, and this is the maximal. So together, you just get 48. Of course, it is a very basic example, but it's true always. Is it clear so far?
Yes.
Okay. Now, I don't have much time because we have started a little bit late, and you want Tomer to take the control, but we have, I mean, maybe 20 minutes. Okay. Let me tell you, okay, that we are going to talk about later that cryptography basic algorithms like RCA and etc. They are all based on the assumption that it is a hard problem to factor a given number to primes. I mean, the algorithm that you need to get this decomposition, okay, is sub-exponential. So if you start with a very great prime, a very great number, okay, you will not be able to decompose it into primes in a reasonable period of time, okay?
Yeah.
Okay. So this is an introduction to what we call Euclides algorithm. Okay. So theorem. Okay. If, okay, given to any A, B naturals, okay, if the GCD is D, then there exists an integral combination of A and B that gives you D. Okay, this is a very important theorem. This is by Euclides. So you see, it's very classical. When we go 2,500 years ago. Okay, Euclides. Okay. Now, the proof of this theorem is also important because it's constructive. I mean, we're gonna see in practice, how do we find these K1, K2? Okay, I'm reading it again. For example, in the last example, we had 8 and 6 was GCD was 2. Okay, so this is very easy. We take 8 minus 6, it's 2, and that's all. So the combination here is 1 and minus 1. But in general, it's not so easy to find K1 and K2. But there exist K1 and K2 integers, okay, that their combination of A and B gives you their GCD. Okay, so let us see the proof, which is called the Euclid algorithm. How do we find these K1 and K2? Okay, so what we are going to do is take A and assume that A is greater than B. Okay, one of them are bigger than the other. So we write A is B times Q1 plus R1, such that, of course, I mean, we took as many B as we could from A, which means that now R1 is less than B. This is the remainder. This is why we call it R. This is the remainder. For example, if we take 8 and 6, okay, so 8 is 6, 1 plus 2, okay? Okay, and then we take B, okay? We always take a recursion. I mean, we take B, okay? And we do the same thing with R1. And we are continuing in this progress. Okay, we take now R1 is R2 plus are 3. Okay, we continue with this progress until we get that the remainder is 1. Sorry, until we get that there is no remainder. Okay, for example, if we've started by A and 6, okay, the next will be 6 is 2 times 3, and that's all. Okay, so here R is 0. So let us write it. And I write the stage, the last stage before we get it.
It's RK minus 3, no?
No, this is
No, yeah, sorry, yeah, it's okay.
Now, once, and it must get to the situation finally, okay, because this number, okay, are decreasing and positive. So finally, you must be able to get to this situation. And the claim is, okay, that this number, okay, which is the last one not being 0, this is the GCD of A and B. So I don't have the time to prove it. I will prove it next week, but let us see one running example, okay? So we see how it works, and maybe Tomer will show you other examples, but we are going to prove it. Okay, so let us see some example. Give me 2 numbers.
1 billion and 1.
You want to stay with me, okay? No? Two numbers, okay?
22 and 17, no, 16.
Okay. So 22 is 16 only one time, plus 6. Now 16 is 6 2 times plus 4. And 6 is 4. See that I'm always writing the Q in this place. Okay, not to be confused with the previous remainders. Okay, so this is 1 times 4 plus 2, and 4 is 2 times 2. So this is the GCD. But we haven't seen yet how to construct from this the integral combination K1 and K2. Okay. So I'm going to show you how do we construct them. Okay. How do we construct K1 and K2? How to find K1, K2. So we are going back from here. Okay. We say that 2 is actually 6 minus 4. And then we are going up. Okay, we have 6 and 4. These are 2 remainders, but the more late one is 4. You see, it is below 6. So instead of 4, I'm going to write 16 minus 2 times 2, 6 times 2. This comes from here. Okay, so instead of 4, I've written 16 minus 12 in this way. Okay, so now I can get together all coefficients of 6. How many do we have? We have 1 times 6 here and 2 other here. 2, you see it's positive. So it's 6 multiplied with 3 with minus 16. Let us see that we didn't do any error. 18 minus 16 is 2, okay? So it's okay. Now I have 6 and 16. 16 is already the queen, okay? If this is the king, this is the queen, we reach the queen, but we still have to get rid of this remainder. Here it is. So this is the last stage. Instead of 6, we are going to involve the queen and the king. I mean, writing 22 minus 16 multiplied with 3 minus 16. And now we get together. Now we get only the queen and the king. So it's going to be 3 times 22 minus how many 16s? 4. Let me write in the as we wrote. This is the combination that gives you 2. Let us see that we didn't do any error. Here we have 66, and here how many we have? 40, 64. Okay, so this is the combination. We have K1 is 3 and K2 is minus 4. Okay. In this way, we produce the integral combination of 22 and 16 that gives you the GCD. And this is very important. We are going to see that cryptography and attacks on cryptography are based on this algorithm. Okay. Okay, but time has ended. So we are going to get back to this, okay, next week. I hope that I see you all, okay, next week. I'm Idan.
Yeah.
I think that the file is going to be too great. So if you can put it on the YouTube, you know how to do it?
Put what? Yeah.
Put the record on the YouTube and send me.
Yeah, so it's going to be in my computer, not yours?
No, it doesn't matter on in any computer. I mean,
No, but it's going to be okay.
you just put it on the YouTube and send me the link, and so I publish the link.
I can put it even in OneDrive or something like that because
Okay. So thank you very much for listening, and see you next week. Okay, Aviv, Erel, Idan, Ocean.
Thank you.
Thanks, yes.
Bye.
Bye.